So welcome everyone to CASA's board meeting on September 7th, 2023. This presentation is in support of CASA's Rover 3 project. The purpose of these presentations is to explain two key information sources being used by the Rover 3 project team to develop their recommendations. The team is relying on several information sources for the report, but the results from the Opus data collection and the modeling work from ICCT are especially relevant. The team feels it is important for the board to be familiar with and to understand the information used to inform their recommendations. Tim Dahlman of the International Council on Clean Transportation and Niranjan Desio of Opus are our presenters today. Tim will give the first presentation on their report from March 2022 entitled Heavy Duty Emissions Control Tampering in Canada. Tim has been a member of the Rover 3 project team since 2018, and ICCT has generously contributed $100,000 to the Rover project team, which allowed us to collect significantly more data than we would have been able to otherwise. Niranjan will give the second presentation, which summarizes the results of work Opus inspections completed for the Rover 3 project team. Their report was recently approved by the project team and is now publicly available on CASA's website. It's worth noting that the conclusions and recommendations from these two reports are those of ICCT and Opus and not the project team. These works will contribute to the project team's recommendations, but those recommendations are still under development. We'll have Tim's presentations first and then go to Niranjan's and have a Q&A in between both. Well, it's still kind of fresh in your and so with that, Tim, if you're ready, please take it away.
Great, thank you so much for the introduction. Just want to check to make sure that everyone can hear me okay before I move on. Great, I'm going to go ahead and share my screen then. I'll just confirm again that the slides are coming through. Great, I see some thumbs up. So I'll go ahead and get started. So first, I just want to thank CASA for the invitation to speak today here at the board meeting. I will be presenting on some research that my organization, the International Council on Clean Transportation, has done in the past few years on investigating heavy-duty emissions control tampering in Canada, including a modeling study that we did to investigate the air quality and health impacts of various tampering scenarios. So before I get started, I just wanted to give a quick overview of my organization, the ICCT. We're a nonprofit research organization that was founded in 2001 to provide unbiased, independent research and technical analysis to environmental regulators with the mission to improve the environmental performance of and energy efficiency of transportation sources. We typically work directly trying to provide regulators and lawmakers with unbiased research and analysis to support better policymaking. In the last 5 years, we worked on various policies around the world and supported the implementation of 48 distinct regulations and policies. The other relevant initiative that the ICCT is involved with that I wanted to note here because of its relevance to the Rover 3 work is something we call the Real Urban Emissions Initiative. So this initiative was founded in 2017 as a partnership between the ICCT and a partner organization, the FIA Foundation, with the explicit goal of using real-world emissions data to better support cities around the world to address high vehicle emissions. And this is really, I think, connected well to the Rover 3 work in that we use remote sensing to measure vehicle emissions around the world, and really was how we initially got in discussions about supporting the Rover 3 project. So since 2017, through the TRUE initiative, we worked with cities, as I said, around the world, starting with London and Paris, and moving on to work with Brussels, Warsaw, Delhi, Seoul, Jakarta, New York City, Mexico City, and upcoming work in Bogota and Sao Paulo. So we appreciate the opportunity to also get involved in the Rover 3 project and do our part to lend some of our knowledge and a network to support the work of CASA. But what I primarily want to be talking about today and have been tasked with presenting to the board here is the results of a study that the ICCT did and published in 2022, looking at tampering of heavy-duty engine emission control systems and their impacts on air quality and health. So this work was funded by Environment and Climate Change Canada, who provided a grant to the ICCT to perform research and analysis on enhanced emissions verification, including the study I'll be talking about today, as well as the funding for the ICCT's contribution to the remote sensing study that was done in support of the Rover 3 project. So before I get into the results of our heavy-duty tampering study, I want to note, as was mentioned by the chair, that all views expressed here are those solely of the International Council on Clean Transportation. I also wanted to note all of the co-authors from the ICCT and others who contribute to the preparation of the report listed here. They really were the ones who did all of the work. I'm just the messenger of some of the results and findings from that work. So just to start off with some high-level objectives of what we're trying to do with this analysis, we really wanted to provide a holistic assessment of the issues that motivate and facilitate tampering with emission control systems of heavy-duty vehicles in Canada. And we set out to do that in a few different ways. So that included reviewing the current regulatory landscape for both provincial and federal tampering legislation. We wanted to investigate what the technology vulnerabilities of modern heavy-duty vehicles were to tampering, and really learn more about what avenues were available for folks, owners of vehicles who were pursuing tampering to limit the effectiveness of emission control systems. In line with that objective, we also wanted to look at those actors who are providing the devices that are used to tamper with vehicles, as well as the services to install those devices through a market assessment, and then also learn the perspective of fleet operators. So we reached out directly to fleet operators to learn more about their perspectives on tampering and the potential motivations and avenues that different stakeholders could take to try to prevent tampering. And finally, kind of the bulk of the work that we did was to conduct a modeling study to analyze the emissions and health impacts of heavy-duty vehicle tampering, to really try to assess what the impacts would be on both air quality as well as residents' health when it comes to what we've seen based on the tampering study that we've been doing. So I'm going to lead just with some key findings. We'll come back to these later, but I wanted to provide them here just to frame some of the slides I'll be presenting after this. We found that anti-tampering legislation in Canada is insufficient. There's a lot of opportunities that exist for folks to pursue tampering without fear of repercussions. Secondly, we found that tampering devices are readily available by well-established providers. So again, for those deciding to tamper with their vehicles, we found that there was a lot of avenues available for them to do that. Thirdly, tampering leads to a substantial increase in pollutant emissions. So the results from our modeling study really reinforced that there are significant impacts, and increased prevalence of tampering can really lead to very substantial increases in harmful pollutant emissions. And finally, those emissions lead to severe health impacts. So tampering is not a victimless practice. There are real-world outcomes and negative impacts on people's health. So just to get started, I just wanted to start out with kind of an overview of the architecture of modern diesel engine emission control technologies, how these technologies work to greatly limit pollutant emissions impacts, and how, if they're not working effectively, how the emissions can increase greatly. So on the right side, the plot shows the progression of federal emission standards in the United States, which are followed by Canada for heavy-duty vehicle engines over time. On the x-axis shows the emission limit for nitrogen oxide pollution, or NOx pollution, and on the y-axis shows the emission limit for particulate matter emissions. So we can see going from 1988 in the top right corner to the small box near the kind of orient of the axis, where it's labeled by 2010, there's been a great reduction in the emission limits that manufacturers of heavy-duty engines are forced to meet. So there's been over a 90% reduction in both the PM as well as the NOx limit. And the reason why regulators have been able to move forward with these more stringent standards is that there's been great increases in the capabilities of after-treatment control technologies over time as well that have enabled these more stringent standards. So if we look to the left, the diagram shows the typical architecture of a modern diesel engine after-treatment control system. So on the left, the diagram shows starting with the emissions coming out of the engine. Usually there's a few different treatment systems that work to greatly reduce NOx and PM emissions in the exhaust stream. So at the bottom, I've listed the two main control technologies that are used. So a technology called selective catalytic reduction is used for NOx control, and a diesel particulate filter is used for PM control. And when working as designed, these are very efficient systems and can greatly reduce the pollutant concentrations in the exhaust that's coming out of modern diesel engines. But the corollary to that is if they're not working correctly, either through poor maintenance or through direct tampering, then emissions can increase greatly. So if these devices are reducing emissions by 90%, the corollary is that if they're not there or working effectively, emissions can increase by 90% relative to the controlled scenario. So that leads us into what some of the motivations for tampering are. So if there was no benefit to vehicle owners and operators, there would be very low incidence of tampering. But there are a few areas where there's either kind of demonstrable benefits or perceived benefits that lead to a higher motivation for tampering with these emission control systems. The first is operational cost savings. In particular, the selective catalytic reduction system uses a working fluid called urea. So that's something that owners of vehicles and operators need to purchase and keep their tanks full. So that can lead to an annual cost savings of between $1,500 and $3,000 if that was removed from the operating cost for a vehicle. Secondly, there's perception that removing or tampering with these emission control equipment can lead to decreased maintenance and downtime. So there are some regular maintenance intervals for the control equipment, including the particulate filters that are used to control PM pollution, as well as regular maintenance of the selective catalytic reduction system. And finally, there's a perception that the use of these control systems lead to decreased fuel consumption and, of course, higher fuel costs if that's the case. There are minor fuel economy penalties to some of the technologies that are used, including exhaust gas recirculation, which is used to control NOx pollution, as well as the particulate filter system. However, most of these penalties have been offset by the modern ability for engine manufacturers to calibrate their engines to be very efficient and utilize SCR systems for NOx control. So in our opinion at the ICCT, the decreased fuel consumption motivation is not in reality really going to do much given the efficiency savings offered by modern diesel engines. So I talked a lot about tampering in general. This slide gets into some of the more specific ways in which we found that modern diesel emission control systems can be tampered with that will affect their efficiency and ability to reduce pollutant emissions. So that includes anything from direct removal of the emission control equipment, so completely removing the SCR system or the DPF, all the way down to manipulation of the software that controls how these systems operate. So there's a wide variety of different avenues by which folks can tamper and affect the ability of these control systems to do their job in controlling pollution. So that gets us into some of the aspects of the study that we did in order to provide an overview of the legislative background that's affecting heavy-duty vehicle tampering in Canada. So as part of the study, the authors reviewed the current regulations and provisions for prohibiting tampering that exist at the federal level as well as the provincial and territorial level across Canada. And what is summarized in the report is that largely the provisions prohibiting tampering and enabling its detection are decentralized and within the jurisdiction of provinces and territories. And out of the provinces and territories that we reviewed, 5 territories and provinces, including Alberta, do not explicitly prohibit tampering of emission control systems. So there's no explicit regulatory language prohibiting owners from tampering with those emission control systems on their heavy-duty vehicles. And we found only 3 instances, so 3 provinces, British Columbia, Ontario, and Quebec, that have both prohibitions on the books for preventing tampering, but also have mechanisms in place by which they can enforce those provisions. So kind of in our analysis, it's not enough to have language and regulations that prohibit tampering. There also has to be mechanisms in place for the authorities to detect when that tampering is happening and take action against those who have tampered with their emission control systems. So as I said, only 3 provinces have that kind of enforcement in place in the form of vehicle inspection and maintenance programs where emissions are being checked on a regular basis. So in addition to looking at kind of what's in place now, we also reviewed what different types of measures are in place to prevent tampering, both on the legal side as well as the technology side. So starting off here, some of those measures include kind of legal prosecution and enforcement against manufacturers, sellers, and installers of tampering devices. So those companies that are enabling this tampering to happen. It includes also, as I mentioned, technologies. So on the manufacturer side, technologies to make it more difficult to impact or manipulate both the hardware and software that's included in both in the diesel engines as well as their emission control equipment, as well as technologies to help to identify when tampering is happening. So if there is manipulation of either the hardware or software happening, making it easier to identify when that's the case. Moving down the list here, we also identified the potential to enforce financial penalties for operators of tampered vehicles. So again, making it riskier for owners and operators to decide to pursue tampering if there's a risk that the benefits that they may get from cost savings of their tampered vehicle, if that's going to be offset by financial penalties if they get caught, it might be demotivating for them to move forward with that tampering. And finally, the last 2 bullet points refer to mechanisms by which government authorities and officials can more easily identify when tampering is happening, either through heavy-duty vehicle inspection and maintenance programs that include regular testing, or through application of roadside measurement and inspection to more easily identify instances of heavy-duty vehicle tampering. So with that background, I want to transition now into the modeling work that the ICCT did in order to try to quantify the impacts of heavy-duty vehicle tampering. And this slide just shows the approach that we took. I'll walk quickly through each of the pieces here. So the ICCT maintains 2 models that we use and regularly update in order to model vehicle emissions inventories and the impacts of different policies on emissions, which we call the roadmap model. And then the second piece in blue on the right, which we call the FATE model, is another component of our modeling infrastructure that's used to take the results from the roadmap model when it comes to the changes in emissions from a specific policy or scenario and translate those into changes in ambient air quality concentrations and on health impacts. So together, the roadmap and FATE model are able to look at different emission scenarios where, for example, we can look at if Canada were to implement new emission standards for heavy-duty vehicles, we could look at how that would impact total emissions over time, and consequently how that would impact air quality and ultimately human health. So each of the other pieces in beige show some of the input data that we fed into the model. So on the left, we have emission factors for various vehicle technologies and ages and emission control level, as well as the impact of tampering on those emission factors. We have assumptions about the incidence of tampering, so how frequent and what percentage of the fleet is assumed to be tampered with, as well as fleet inventories and fleet activity data at the provincial level. So that all feeds into the model, and output includes emissions projections over time at the provincial level that get translated into further inputs to the air quality and health modeling features of the architecture. And finally, on the right, after those modeling steps are taken, we're able to look at, like I said, the impacts on human health from various different emissions scenarios and projections. So one of the key inputs to this study really is the tampering incident. So how frequently and what percentage of the fleet can we consider to be tampered with? And this is a really hard data point to come by. There's not a lot of information out there, and one of the reasons why, kind of in our opinion, the Rover 3 study has been really a valuable resource, and that is actually providing some real data that can be used to inform these types of studies. Unfortunately, the data from the Rover 3 study wasn't available to the ICCT when we did this analysis, so we had to try to come up with a different approach to trying to define the prevalence of tampering in Canada and in individual provinces. And with our approach, since there was really a lack of data at the time we were doing this work, we tried to look at a couple different scenarios to provide a range of what the impacts might be under different scenarios and different levels of tampering. So this slide shows the 4 different scenarios that we modeled in our work. So we started with the counterfactual, which was a case where we assumed that there was no tampering. So in that case, we assumed that all of the trucks on the road were meeting emission standards and that the emission control equipment was operating as expected and as intended. So in that case, you can see that the incidence of tampering in Alberta and nationwide is assumed to be 0%. Then for a medium tampering scenario, so I'll jump to the medium tampering scenario, was kind of our starting point, where we decided to look to some recent work that was done by the U.S. Environmental Protection Agency. They published a fairly detailed report on the incidence of tampering in diesel pickup trucks or diesel medium-duty trucks in the U.S., presented some data on a state-by-state basis. So we based our kind of our medium level scenario on the results from that analysis by the EPA. In that case, we assumed 22% tampering incidence for medium-duty trucks nationwide and a 7.3% incidence for heavy-duty trucks. And in Alberta, we have slightly higher assumptions given the lack of any prohibitions against tampering in the province. We assumed a slightly higher incidence, so 30% for medium-duty trucks and 10% for heavy-duty trucks. And then on either side of that scenario, we have a low and a high tampering scenario where we adjusted those assumptions either up by 1/3 or down by 1/3 to provide a range of estimates. So this slide is quite detailed, so I'll just try to point out a few of the key features rather than try to explain the whole thing. Essentially, this shows our results and our estimates of excess emissions from tampering in 2 years, in 2010 and 2019. So in this case, we're showing results for NOx in the left-hand plot and PM in the right-hand plot. And we're showing the results for each year at the provincial level. So one feature I really want to point out to start is just in all cases, emissions decreased from 2010 to 2019. And that's really showcasing the effectiveness of the modern diesel control system. So new vehicles sold into the market in 2010 were required to have both diesel particulate filters and SCR systems, and the combination really is effective at reducing emissions. So you can see absence any tampering, the implementation of those new technology packages really reduces emissions of both NOx and PM. But the other thing to point out is in blue, so if we just focus on the far left-hand plot, we can see that the blue is showing the excess emissions from tampering for each province in 2019. And that's really, as the entire fleet emissions is reduced through the application of these advanced control technologies, the importance of tampering becomes much greater because you have 90% of the fleet that's very clean, but those tampered vehicles have much higher emissions and are driving a much larger portion of the inventory. So in our research across Canada for 2019, we estimated that just the amount of excess NOx pollution alone coming from tampered vehicles in our medium scenario is equivalent to adding about 220,000 additional trucks to the Canadian fleet. So the emissions level is the equivalent of that of 220,000 additional trucks entering the fleet, just to provide some context. So in addition to looking at estimates of past years, we also look forward in the future of what the impacts of tampering might be as we continue to overhaul the fleet and introduce more stringent emission standards over time. So this shows the results from that exercise, looking at projected emissions between 2020 and 2040 for NOx on the left and PM on the right for the province of Alberta for each of the different scenarios. So the brown line shows the counterfactual scenario. So again, kind of in the case where the assumption that there is zero tampering going on. So in that case, we can see that the implementation of these, both the existing standards and improved standards over time, greatly reduces both NOx and PM emissions to near zero levels. However, in the tampering scenarios, even the low tampering scenarios offset much of that potential emissions reduction. So we found that in the low tampering scenarios, PM pollution could be about twice as high as a counterfactual example, and the discrepancies were even larger for NOx emissions on the left, where we saw emissions could be up to 6 to 7 times higher under the various tampering scenarios. And those excess emissions have impacts, not just on air quality, but also on health. So this plot shows our estimates of the differences in premature deaths in the top plot and disability-adjusted life years in the bottom plot for the different scenarios that we included in our modeling exercise. So we can see on the top, just focusing in on the estimated premature deaths from emissions from heavy-duty vehicles in Canada, the implementation of new emission standards, existing and new emission standards, greatly reduces the health burden of heavy-duty vehicle activity in Canada under the assumption that there's no tampering going on. So if we look at that brown line, we see the number coming down from about 423 in 2020 to around 65 in 2040. However, again, if there's tampering happening, even in a low incidence scenario, those health impacts increase greatly. So from 65 to up to around 474 in 2040 for the medium tampering scenario. And the last slide I'll show on the modeling study is just some work that we did. So since there is such a great level of uncertainty in the actual tampering incidence rates, we decided to present some results that were just looking at the impacts if there were to be a 1% increase in tampering. So instead of kind of trying to figure out the exact number, we said, well, what if there is just a 1% increase? What would the impacts be? These results show the impacts, and we can see, just again, focusing on the far left-hand set of plots for Alberta, in 2040, just a 1% increase in tampering can lead to a 54% increase in NOx emissions and a 15% increase in PM emissions. And this also speaks to really the need for studies like Rover 3 that are actually trying to quantify what this incidence is and to provide some real world information that can help to support better estimates of both the emissions impacts of tampering as well as the health impacts. So in closing, I just want to reiterate some of the key findings from the study that I presented here today. First, again, from our viewpoint at the ICCT, we consider tampering legislation in Canada to be insufficient. Just to reiterate, Alberta, as well as many other provinces and territories, either lack the statutes prohibiting tampering or have not yet adopted provisions such as inspection and maintenance programs that enable enforcement of those prohibitions. Secondly, we found in the course of the study that tampering devices are readily available by well-established providers. In particular in North America, popular approaches include both a combination of hardware removal, so actually removing pieces of the mission control system itself, or manipulation of the software that is controlling the actual operation of that control equipment. Thirdly, the tampering, from our modeling study, we were able to demonstrate that tampering leads to a substantial increase in pollutant emissions. So again, in 2040, each 1% increase in tampering is modeled in the study to result in emissions increase of PM of 15% and NOx of 57%. And finally, tampering is not a victimless practice. So again, kind of the study was able to quantify the health impacts of different tampering scenarios through 2040. And we estimated that each increase in tampering incidence of 1% leads to 690 excess premature deaths over the next 20 years. In closing, I'll share here the policy recommendations that were put forth in the ICCT study, and just I'll reiterate again, these are the perspective and viewpoint of the ICCT as an international independent expert organization. So the first is we recommend that Canada should explicitly prohibit tampering at the federal level. The approach now leaving decisions to each province and territory we found to lead to a patchwork approach that hasn't been effective in discouraging tampering. Secondly, steep penalties should be set for the providers and users of tampering devices and services to, again, discourage that as a route to manipulating the engine and control equipment. We found that inspection and maintenance programs can be an effective way to address tampering. So requiring regular testing and inspection of vehicles, again, provides another barrier to folks who might be pursuing tampering options. As I mentioned earlier, remote sensing and other roadside emission inspection methods can be used as a way to identify when tampering is happening outside of the normal inspection and maintenance program requirements. And the last 2 points here speak to kind of future emission standards being used as a mechanism to drive the adoption of technologies that can prohibit or make it more difficult to tampering with engines and emission control equipment. And finally, I put this in bold because I think it speaks to the presentation that Niranjan will be giving. We really think that there should be more research and study of the prevalence of tampering in order to close a knowledge gap and provide the information that can support the implementation of these various policy recommendations. So with that, I will close my presentation and again, thank everyone for the opportunity to present here today and for the opportunity to be involved in the Rover 3 study. So thank you.
Thanks very much, Tim, for an excellent presentation. Our next presenter, our presentation is Niranjan. If you're ready, Niranjan, just take it away.
Hi there, everyone. Thank you again for having me, Tim. I'm sorry that you'll probably have to leave, but great presentation, Tim. I see some familiar faces out there. Hi, everyone. It's hope it's nice and cool up there, Andre, Katie. Like Tim said, I am given the pleasure of giving this presentation. I didn't do all the hard work. I did a little bit of it. It was a pleasure being up there in Alberta, collecting some of the data and touring some of your national parks in the process. So can you guys see my slide?
Yes.
All right, here we go. Oh, hang on. It did not advance. Let me try it over here. Okay. It's the outline now, right? Very good. I'm advancing. So I'll just do a very quick, one slide recap of the introduction background for this project. I think you're amply familiar with it. I don't need to tell you why we did it. The method, many people have been hearing me drone on for 5 years about remote sensing, like Anne, like Rob, Katie, Andre, so you know what remote sensing is. It will be brief for the uninitiated. Then we'll get into the results. I'm trying to present the results from the Alberta study in the context of a couple of benchmarks or a couple of frames of reference. One is the actual standard, the Canadian standard, the certification standard for these vehicles, and a comparable fleet. In the case of light-duty vehicles, it was Oregon, heavy-duty vehicles, California. Okay, then we'll drill down a little bit and look at a particular type or two that are contributing disproportionately. Okay, I'll do light-duty vehicles first and then heavy-duty. And if necessary, I'll pause after light-duty and we can take some questions or we can just move right ahead. All right, so here's the background, and you know it just as well as I do. CASA had a non-point source report, we call it mobile sources, that was done a few years back. Within that report was projections or estimates from a air pollutants emissions inventory, and that indicated that heavy-duty diesel vehicles and then light-duty gasoline trucks were a large source of nitrogen oxides. Those gasoline trucks were also a source of hydrocarbons, and then those heavy-duty diesel vehicles were a particular source of particulate matter. Okay, and so that was the motivation for CASA contracting with us, and we did the light-duty vehicles and heavy-duty vehicles in different years. 85% of the data we collected for light-duty was in 2021. There was a little bit collected in 2020 when we came up to scope things out. And then we went back and collected about 10% of the data in Fort McMurray for the light-duty vehicles in 2022. All of it was in 2022 for heavy duties. Okay, they were previous rovers, but they were with older technology and they only focused on light duty. All right, light-duty vehicles. I think this is familiar with you. This is what remote sensing looks like. It's going to be a very brief method overview. We did it in Calgary. The devices are in those boxes. They're at the level at which most tailpipes, light-duty tailpipes, emit. We did it in Red Deer, sometimes with 2 devices at the same place, sometimes 2 because these are unattended at different places. We did it in Edmonton, Grand Prairie, and then Fort McMurray. A nice robust data collection, almost 50,000 good measurements that we could use in analysis. Unlike or much like the United States, it's mostly a gasoline fleet. It's about the same percentage here, maybe even 96. All of these were Alberta vehicles, largely. You don't have a lot of invasive species, so to speak. And the bulk of these are light-duty trucks. That was a little higher than what we find around here. More light-duty trucks for you guys than down here. Okay. Okay, comparing to benchmark emissions. Now these are, I call them benchmark emissions because they're not the exact standards. We had to make some assumptions to get everything into common units. And it leans towards the newer standards over this broad range. The range I'm talking about is the 2003 and newer models. That's what we focus this particular analysis on. And that's because they represent the bulk of the vehicle kilometers traveled. Okay. I should say for carbon monoxide, this is not an unusual result. I should say you can see the line across right around 1.4 grams per kilometer. That's where we've placed our benchmark standards. Having excess emissions above the standards in itself is not an indictment of the vehicle. Vehicles can emit twice, 3 times, sometimes even 4 times, depending on the climate, depending on the road network, the driver behavior, and so forth. It's just when you get egregious exceedances of the standard that we start raising our ears or raising our eyebrows. The NO, 37% of our observations in this particular case were above the standard. Again, I don't get extremely concerned until I see 8, 10 times. And if I can move my cursor, there's very small fraction that would be 10 times above the standard. Hydrocarbon, slightly different story. Right off the bat, you got the majority of your observations above the standard. But here's where things start getting of concern, because as much as 10% of the observations were 10 times the standard. And that's when we start questioning whether there's been significant malfunctions or maybe even some tampering going on. Is 10 times a magic factor? No, I'm going to give you some perspective. This is looking back. This is a slide from my 2017 presentation after everything went down with Volkswagen. We weren't looking for Volkswagen emissions. We were doing our thing in the United States. We went backwards and looked retrospectively at what they looked like in our data. And what you're seeing in the colored lines is each line is a model year of the Euro 5 2-liter diesel. Very few of them, but they were in our data set. And as they were measured in each of the measurement years. And the only takeaway is, on average, they were about 10 times their applicable standard. Okay. It wasn't until those culprit lean NOx traps, which were insufficient, were being replaced with these selective catalytic reduction systems. That's when the emissions started coming down. They started doing that in 2014, and they had done most all of them by 2015. Okay. Next frame of reference, I'm comparing Alberta to Oregon. Why Oregon? Measurements happen to have been done in 2022 with similar technology and about the same data size, the database size. And it gives us 2 frames of reference. Oregon has an inspection and maintenance program, but only in the areas that don't meet the National Ambient Air Quality Standards, which are around Portland, in this gray shaded area, and around Medford. So we did collect for Oregon data within the IM area and outside the IM area, so you get a comparison to 2 subfleets. Here's the CO. As you can see, the dark blue on the left-hand side of each group is Alberta. They were above, on average, the Oregon inspected vehicles as well as uninspected vehicles. A little bit bigger of a difference for NO. And then for HC, the largest difference of all, and that follows with what I just showed you in the exceedances of the standard for HC. So this is where the largest difference was. And all these differences are statistically significant. Alberta also exhibited a much higher rate of high emitters. In this particular case, we're judging high emitters by these standards if they're an exceedance of the. Well, by the way, are you able to see my cursor when I move it around? Okay, okay. I just want to make sure I'm not just fooling myself. High emitter in this particular case is above those levels. So a much higher rate in Alberta, and the differences were statistically significant at the 95% confidence interval. Okay, I'm drilling down into contribution, and then I'm going to get into a particular type that was of concern, vehicle type. Here's where you got validation of the vehicle kilometers traveled. These are 4 groups, okay? It's, in this particular case, I have the oldest, of 1997 and older. I have a group of 5 years, 1998 to 2002. A 10-year group in the green, and then the newest 10 years, about 2013 and onward. And that's from the perspective of when we did this work. Okay, so these 2 groups, the 20 years and newer vehicles, represent the bulk of vehicle kilometers traveled. They're the ones polluting. And they represent a proportionally smaller fraction of the overall emissions. That's to be expected. They're the newest vehicles. They may travel more than their contribution to the overall inventory. But it was a little surprising from our perspective and from our point of view from here in the US to find the latest 10 model years contributing over 50% of the fleet's hydrocarbon emissions. That's a little higher than we would normally see. But if you're looking for disproportionality, who contributes disproportionately, it's the second 10 years, 2003 to 2012. They're only 30% of the vehicle kilometers traveled, but they're contributing disproportionately or proportionally more of the NO and hydrocarbon emissions. Okay, final look on light-duty emissions by body type. And we're only looking at hydrocarbons and NOx. Those are the pollutants of concern from an ozone standpoint. One thing that's clear, not that different from the US in most everywhere we test, is that the trucks, the light-duty trucks, are higher than cars. There's three categories that fit into the category of trucks, and that's pickups, SUVs, and vans. We've got them broken out. So one takeaway from this was that what I'm calling older middle-aged trucks, this 2003 to 2012, they were significantly higher than the rest. So in terms of a area of focus or a contribution, these trucks seem to be contributing a fair amount of the light-duty pollution. And that seems to corroborate what the emissions inventory of 2014 suggested, where they estimated that the light-duty gasoline trucks are a large source of HC, certainly, and to a lesser extent, the NO. Okay, and these are the pickup trucks that look like the highest in this particular case. Okay, so to sum up light-duty gasoline vehicles, the majority in the case of hydrocarbons, you saw that 55%, the majority were higher than the Canadian benchmark standards. But of particular concern is that as much as 10% were well above the standard, in this case, 10 times. Areas of where we start suspecting malfunction or even perhaps some other intervention. Alberta is much higher than Oregon's inspected fleet. That's not unexpected, but also higher than the uninspected vehicles. These are the ones that never go in for their biennial inspection. Much higher rate of high emitters, and a little bit surprising that the latest 10 model years do contribute over 50% of the hydrocarbon. Okay. Pickup trucks were the ones we identified as the highest contributors in this particular case of the hydrocarbons and NOx, and that corroborates the inventory. So one of the things we'd recommend is if, I know there's no inspection program, and all the inspection programs in the US focus on OBD, onboard diagnostics, maybe an awareness campaign to promote check engine light response might be helpful. And of course, we do advisory programs, but sending out some notices, advisory notices, might also be an option to make people aware of their high emissions and that things can be done about it. On to the heavy stuff, the fun stuff. Okay, method was a little bit different. You saw those remote sensors nicely packaged in green boxes. They have batteries. We can leave them unattended. The way it's done is a little bit different. We've got to place a sensor low and a sensor high. Here's a better example of the picture of Airdrie. So the point here is we did 6 vehicle inspection stations. And I should also say, we did a reboot partway through planning our program. We were looking to do heavy-duty vehicles along with light-duty vehicles at typical on-road sites. And I'm glad we reset because we got a lot more data focusing on heavy-duty vehicles at these vehicle inspection stations. We got a lot more data. So yeah, Coutts, Airdrie, 1 high, 1 low for the downdraft, for the updraft, Leduc, Whitecourt, Atmore. Places like Atmore were quite interesting, as well as Demet, where we had a very enthusiastic sheriff who was keenly interested in our data. That's because there was some vehicles that I never knew existed passing by. So very interesting oil and gas vehicles, and it was quite illuminating. As I said, we collected much less than light duty, but surprisingly a good number, over 6,000 measurements of heavy-duty vehicles. And believe me, the equivalent effort at light-duty sites might have gotten one every 5 minutes, or it would have been much less. So I'm glad we focused at vehicle inspection stations. 97% diesel, not a surprise. 83% Alberta registered. Also, I'm not sure if that's a surprise to you, but no, not that much of a surprise, and most of them are tractor trailers. Okay, I have this slide because unlike the light-duty vehicles, which were all Alberta, you got a significant population. 17% of the observations here were of heavy-duty vehicles from other places. So you got a fair amount of other provinces contributing. Okay. And then in some places, in some vehicle inspection stations like Airdrie near Calgary, a fairly sizable population of dump trucks. Okay. We specifically went through every image to make sure we were classifying it appropriately, but that's a dump truck, that's a tractor trailer. And then we do see at these vehicle inspection stations, these delivery trucks come by and even a pickup truck, but just to assure you, we weren't including those in the analysis of heavy-duty vehicles. But I guess they come by to check their weight. Okay, comparing them to benchmark standards. Not surprising, they're not in exceedance of the CO standards, but diesels don't put out CO. In fact, they really don't put out hydrocarbons either. And by the way, we're focusing on 2010 because largely 83% of the observations, and that's an akin to vehicle kilometers traveled too. Bulk of these are, 2010s are responsible for the bulk of the kilometers traveled. Here's hydrocarbons, a little bit of a surprise, but again, I don't get nervous until I see exceedances by multiple times the standard. 45 is larger than I would have expected, especially at the low power range that we were measuring. But here's where things get a little more interesting. Okay, particulate matter. Now, I'll be quick to point out that we are not sucking exhaust onto a filter and weighing it. This is not a weight of black carbon. Ours is an optical technique, naturally, because we're measuring vehicles as they go by. And so in technical terms, it's fuel specific, but it's an estimate. Okay, we're using extinction coefficients, how much black carbon extincts light to estimate how much black carbon there is. Okay, so it's not a direct PM measurement. But when things are above 10 times, yeah, it's starting to indicate something unusual is happening with the vehicle. It's NOx that was of a surprise because 30% of our observations were well above the standard, in this case, 10 times. Okay. Now, I'm not suggesting by this that 30% of the vehicles right off are tampered. Okay. We did not stop any vehicles. We're not inspecting any vehicles. These are the results of the measurements. To have 30% of the measurements be above the standard at that level is a concern. And so it's leading us to suspect something is happening. Malfunction, unusual deterioration, or perhaps intervention to tamper. So we want to look deeper into this 30%. We said, okay, there's a bunch of vehicles that came by at Airdrie and at Leduc, which were the highest volume VISs. Many were measured multiple times. That gives us more confidence when we measure things multiple times. In this case, the 17 most frequent, vehicles with the most measurements, we looked at those, and right off the bat, when they're well controlled, when a vehicle's working well, as 60% of them were, the NOx emissions are well controlled. They're low. But at least 30% are much more variable and sometimes very high. So it was another indication that perhaps our 30% number wasn't completely off the mark, because we saw 30% of the vehicles that were being measured multiple times, 4+ times, with averages at very high levels. Okay. Here's an example. It happens to be a dump truck, and I hope I'm not exposing anything with the number, but this one came by at 1,500 ppm. It came by again a couple hours later, 1900 ppm. I'm talking about NOx here. An hour later, 1700, 1000. Those are very high levels. Okay, even here. So that's why we're starting to look at this 30%, say up to 30% could be malfunctioning badly or maybe have had intervention of some kind. All right. Comparing it to California. Why? Because California is the longest inspected fleet, the oldest inspected fleet. They've had an inspection program there since the 90s. Again, we're looking at just 2010 and newer vehicles, and we've broken it up into 2 5-year bands. So all these vehicles, 2020 and newer, should have those devices that Tim was talking about. The DOC, the SCR, selective catalytic reduction systems, DPFs, and they should be abiding by the newest standards. And I want to assure you that these were done at different times. California was in 2020, but towards the winter in November 2020, and Alberta was in 2022. So roughly speaking, similar temperatures, and definitely with the same technology. First thing here is Alberta looks considerably higher than the average California vehicle. In some cases, considerably higher. I mean, let's focus on NOx alone. You know, on average, we found that the Alberta fleet of the second half, the 2010 to 2015, again, they were averaging over 10 times the standard. Okay, you can clearly see that California is above the standard as well, but not nearly as high. And I'll end with a couple with this. I think this is my last slide. We wanted to drill down into a couple of the by location and by type. So we're focusing just on NOx. That's become the problem pollutant here. What you'll notice is the Demet fleet is by far the dirtiest in terms of NOx emissions, but there were also very few vehicles in these very specialized vehicles, so I guess I wasn't surprised. Atmore also, well, in this particular case, Atmore was the lowest. It also had very few observations, very few vehicles, so probably not a huge concern from an air quality standpoint. Coots, where it was predominantly long-haul tractor trailers, was also fairly low, second lowest, but it really was the newest fleet, and so I'm not surprised at its level. Airdrie is where the concern is. It's closest to the highest population area, I believe, of Alberta, near Calgary. And it's concerned because it's got the oldest fleet, it's got very high NOx emitters, and it's got the largest population of dump trucks that we observed, which is, as you can see, a much higher NOx fraction of the fleet. So you got probably the worst type of vehicle, the highest emitter in a high population area, and there's lots of them making many, many laps, as I showed you earlier with the cascading picture of that one dump truck. Okay. So to sum up heavy duty, I'm surprised to see this many of the observations well above the standard, 30% above, more than 10 times the standard, a little less for PM. And that's where we really suspect malfunctions or tampering. The 10 newest model years, 2010 and onward, maybe 12, a significant portion of them, this represents the most vehicle kilometers traveled, and they were significantly higher than California's. The second half, the 2010 to 2015, they average 10 times the standard, so that's of concern. But this is all corroborating what your inventory estimated, which is heavy-duty vehicles are a significant source of NOx. But I will tell you that these dump trucks, I saw the highest. Clearly, the data corroborates it, and it's of concern when they're traveling up and down the central corridor between Calgary and Edmonton. So one thing I can see happening is remote sensing being used at the VIS stations to flag the ones that are very high. When they go into their secondary inspection behind a little police station, take a look. take a look at what might have happened, whether there's any tampering going on. Some good visual inspection can be done. And then, of course, anti-tampering legislation, which I believe is lacking, which Tim adequately pointed out, should be in place. So with that, we'll end and give you a chance to ask more questions.